All right, so we are still doing Laplace transforms. And we've defined Laplace transform of f to be the integral from t goes from 0 to infinity of f of t times e to the minus st dt. And we now know this is a function of s. There's no t involved in this anymore. We know the Laplace transform of t to the n is n factorial over s to the n plus 1. Laplace transform of e to the at is 1 over s minus a. And we have nice other things, properties about this. I'm not going to go through now just because of time. It's important to recognize that the square root of minus 1 is a constant. It has not changed for a very long time. So we can treat it as a constant. Why is that important? If I take the Laplace transform of I, because it's a constant, I can just pull it out. And it's I times the Laplace transform of 1. So it's I times 1 over s. Right? Likewise, if I look at the Laplace transform of 3i times t to the 8th, this is a constant, so I can pull out the 3i. So this becomes 3i times the Laplace transform of t to the 8. And the Laplace transform of t to the 8 is going to be 8 factorial over s to the 8 plus 1, or s to the 9th. And notice I'm not messing around with these factorials. I'm just leaving them be. It's going to be very important to leave factorials and things alone, because it's going to make it much easier for you to identify patterns and how things vary when certain parameters vary. So just leave it be. It's perfectly fine. Okay, so we have Laplace transform of e to the at is 1 over s minus a. We know that I is a constant, so we are not intimidated by that in the least. So what does that mean? That means if I take the Laplace transform of e to the iat, and now everything in front of the t is just I times a. So instead of a, I'm going to everywhere I see an a, I'm just going to replace it with an I times a. No big deal. So the Laplace transform of e to the iat is going to be 1 over s minus ai. No biggie. I sort of don't like that, though, because I would like to be able to write this in rectangular form. So if I multiply top and bottom by the complex conjugate, so we're assuming s is a real number. In the numerator, I have s plus ai. In the denominator, I'm going to have s squared minus ais. I'm going to have plus sai. I'm going to have minus a squared I squared when I multiply those things. So I'm going to leave the numerator alone. S squared, these terms cancel. I squared is minus 1. So in the denominator, I get s squared plus a squared. I can break this up into two pieces. The real part and the imaginary part. So basically I have s over this plus ai over this. So I have the real part and the imaginary part, and that implies then that the real part of this has to equal the real part of the right-hand side. The imaginary part of this has to equal the imaginary part of the right-hand side. So what do we have? We just found out that the Laplace transform of e to the iat is s over s squared plus a squared plus a over s squared plus a squared times I. So we have a real part and an imaginary part, but we also know from Euler's formula that this is cosine of at plus I sine of at. So the Laplace transform of cosine e to the iat is cosine of at plus I sine of at is equal to s over s squared plus a squared plus a over s squared plus a squared I. I can break this out into different pieces because I'm adding. So it's going to be the cosine of the first term plus, Laplace transform of the first term plus Laplace transform of the second term. But that's I is a constant, so I can pull that out. So the left-hand side of this thing is the Laplace transform of cosine plus I Laplace transform sine. And we just showed that's equal to s over s squared plus a squared plus a over s squared plus a squared I. Notice this is real. This is real. So those two things have to be equal. This is imaginary. This is imaginary. So those two things have to be equal. Okay, so sorry, there was a interruption there. So if we set the real parts equal and set the imaginary parts equal, the Laplace transform of cosine of at has to be equal to the real part on the right-hand side. So we get s over s squared plus a squared. And the Laplace transform of sine of at is going to be a over s squared plus a squared. So we basically get the Laplace transform of trig functions based on what we know about the Laplace transform of exponential functions. So again, Euler's formula comes back to save us. All right. So, where was it? Okay. So let's look at a couple examples. If I have the Laplace transform of some function is equal to 6 over s to the fifth plus 8 over s squared plus 16 minus 3s over s squared plus 9, you should be able to look at this and think it looks like something over s to the fifth. So you should be thinking t to the fourth. If you see something like this, it looks like a constant over s squared plus 16. You should be thinking sine. In this case, a squared is 16. So you should be thinking sine of 4t. And then here, this looks like s over s squared plus 9. And so the a squared is 9, so that's going to give you a is 3. So you should be thinking cosine of 3t. So before you go through and do the algebra to sort things out, you should have a pretty good general idea that you're going to get something that looks like t to the fourth plus something times sine of the 4t plus something times cosine of 3t. The only question now is, what's the somethings? Okay, so what do we know? We know that the Laplace transform of t to the fourth is going to be 4 factorial over s to the fifth. So I need a 4 factorial in this expression. We also know that the Laplace transform of sine of 4t, that is going to be, 4 over s squared plus 16, which means I'm going to need a 4 somewhere up there. And finally, the Laplace transform of cosine of 3t, we know is s over s squared plus 9. And notice there's an s, and there's an s squared plus 9, so we're actually sitting pretty for that. Okay. So let's back up. We were given the Laplace transform of g is 6 times 1 over s to the fifth plus 8 times 1 over s squared plus 16 minus 3 times s over s squared plus 9. And we see s over s squared plus 9 right there. We do not like that. We know that we need a 4 there. I can't just multiply by 4. If I multiply by 4, I have to divide by 4. And here, I know that I need a 4 factorial. But again, I can't just put it 4 factorial there. If I multiply by 4 factorial, I have to divide by 4 factorial with the idea that this whole expression now is equal to my original expression. So what just happened is my original expression looked like this. Because of this t to the 4th, I know I need a 4 factorial there, but I have to divide by 4 factorial. Because the square root of 16 is 4, I know need a 4 there. But if I multiply by 4, I have to divide by 4 to make it equivalent. And I can leave this alone. So this is now 6 over 4 factorial times the Laplace transform of t to the 4th. That's 2. 4 over s squared plus 16 is the Laplace transform of sine of 4t. And then s over s squared plus 9 is the Laplace transform of cosine of 3t. And I can bring everything together. So this is 6 over 4 factorial times t to the 4th plus 2 times sine of 4t minus 3 cosine of 3t. So it's the Laplace transform of that whole thing. So my g of t is 6 over 4 factorial t to the 4th plus 2 sine of 4t minus 3 cosine 3t. So given all of these new formulas, it's really important that you be able to go frontwards and backwards. So if you had been given h of t is equal to 6 plus 7 t to the 8th minus 4 cosine of 2t plus, we've used 6, let's go with 5 sine of 7t. Then the Laplace transform of h is going to be 6 times the Laplace transform of 1 plus 7 times the Laplace transform of t to the 8th minus 4 times the Laplace transform of cosine of 2t, and then plus 5 Laplace transform of sine of 7t. And now I just go down the line and do each piece separately. So this is going to be 6. Laplace transform of 1 is 1 over s plus 7. Laplace transform of t to the 8th is 8 factorial over s to the 9th minus 4. Laplace transform of cosine 2t, so a is 2. It's going to be s over s squared plus 2 squared. I'm going to have 5. Here a is 7, so I'm going to have 7 over s squared plus 7 squared. Okay. Again, don't overthink simplifying things. Leaving things like this is perfectly fine. The more you simplify things, the harder it is. So the word simplify, the way we use it in the math department is the opposite of what it really means. And if you've ever taken a math class, you should not be surprised that we're misleading you like that. All right. And before I go, just so at this point, we have the Laplace transform of f is the integral from 0 to infinity, f of t e to the minus st dt. Laplace transform of t to the n is n factorial over s to the n plus 1. Laplace transform of sine of at is equal to a over s squared plus a squared. Laplace transform of cosine of at is s over s squared plus a squared. And then almost forgot. Laplace transform of e to the at is 1 over s minus a.